This is the first of 5 modules which comprise National Training Center's course on basic DC system testing and maintenance. The first module, Module 1, will cover terms and basics. The objectives of this course are that upon completion, you will be able to explain the basic terminology and theory associated with electrolytic cells, explain DC system safety associated with electrolytic cells and cell lines, describe the acceptance testing procedures associated with electrolytic cells and cell lines, describe the maintenance, inspection, and testing associated with electrolytic cells and cell lines, and finally explain the characteristics associated with lead acid and nickel cadmium batteries. This training is comprised of 5 modules with exams on each module. Completion of the modules will provide the knowledge factors required for the CEUs that will be assigned. Additionally, there are practical factors that must be completed in a lab simulation or on the job. Completion of these practical factors will provide a certification in basic DC systems. This certification means the trainee is capable of executing basic testing and maintenance on battery cells, cell lines, known as battery banks, and chargers. The trainee should follow along in the trainee guide. The exam links are in the electronic version provided. We will begin with some trade terms. Acceptance test. This is the constant current or constant power capacity test made on a new battery to confirm that it meets the specification or manufacturer's ratings. Battery effect. This is a voltage that exists on a cell line after the power supply is disconnected. Capacity test. A discharge of a battery at a constant current or constant power to a specified terminal voltage. Cell line. An assembly of electrically interconnected electrolytic cells supplied from a DC power source. The term cell line can be found in both NFPA 70, the National Electrical Code, and NFPA 70E on electrical safety. This is a term that we see quite often in NFPA. It's also what you may have heard referred to as a battery bank. The technical term is cell line. Cell line voltage. The DC voltage applied to the positive and negative bus supplying power to a cell line. Cell line working zone. The space envelope wherein the operation or maintenance is normally performed on or near energized surfaces of electrolytic cell lines or their attachments. We will go in depth on cell line working zones in module number 2. Critical period. That portion of the duty cycle that is the most severe, or the specified time period of the battery duty cycle that is most severe. Duty cycle. The loads of batteries expected to supply for a specified time periods while maintaining a minimum specified voltage. Equalizing voltage. The voltage, higher than float, applied to a battery to correct inequalities among the battery cells. That would be in voltage or specific gravity, or both. Float voltage. The voltage applied to a battery to maintain it in a fully charged condition during normal operation. Float charge. A constant potential normally applied to a battery to maintain it in a charged condition. High rate charge. The application of a constant potential charge at a higher level than the float charge to a partially or fully discharged battery to recharge it. Flooded cell. The cell in which the products of electrolysis and evaporation are allowed to escape to the atmosphere as they are generated. These batteries are also referred to as vented batteries. Modified performance tests. A test in the as-found condition of battery capacity and the ability of the battery to satisfy the duty cycle. Performance test. A constant current or constant power capacity test made on a battery after it has been in service to detect any change in the capacity. Rated capacity as it applies to lead-acid batteries. This is the capacity assigned to a cell by its manufacturer for a given discharge rate at a specified electrolyte temperature and specific gravity to a given end of discharge voltage. Service test. This is a test in the found condition of the battery's capability to satisfy the battery duty cycle. Terminal connection. Connections made between cells or at the positive and negative terminals of the battery, which may include terminal plates, cables with lugs, and connectors. And finally, the vented cell. A cell in which the products of electrolysis and evaporation can escape to the atmosphere as they are generated, like a flooded cell. We're now going to be in section 2.0.0 of your trainee guide, and we're going to be talking about battery system basics. This is a very rudimentary, foundational, basic concept on batteries to ensure that we have the proper preparation and the proper foundation for going further into batteries as we investigate maintenance and testing and acceptance. This will seem very simple to some of you who are already familiar with how battery systems work and the basics of battery systems. A battery, which is an electric cell, is a device that produces electricity from a chemical reaction. Strictly speaking, a battery consists of two or more cells connected in series or parallel, but the term is generally used for a single cell. A cell consists of negative electrode, an electrolyte, which conducts ions, a separator, also an ion conductor, and a positive electrode. The electrolyte may be aqueous, in other words, composed of water, or non-aqueous, which means not composed of water, in liquid, paste, or solid form. When a cell is connected to an external load or device to be powered, the negative electrode supplies a current of electrons that flow through the load and are accepted by the positive electrode. When the external electrode is removed, the reaction ceases. A primary battery is one that can convert its chemicals into electricity only once and then must be discarded. A secondary battery has electrodes that can be reconstituted by passing electricity back through it, also called a storage or rechargeable battery. It can be reused many times. These terms are a little counterintuitive. You would think that a rechargeable battery would be a primary battery. But in fact, remember, it is a secondary battery. The primary battery is like the D cells or double A's you throw away when you're done with them. A battery stores electricity for future use. It develops voltage from the chemical reaction produced when two unlike materials, such as the positive and negative plates, are immersed in electrolyte, a solution of sulfuric acid and water found in a typical lead-acid battery, for example. The voltage is approximately 2 volts per cell for a total of 12 volts in a typical car battery. Electricity flows from the battery as soon as there is circuit between the positive and negative terminals that happens when any load that needs electricity, such as the radio, is connected to the battery. Now let me expound a little on this 2 volts per cell. That's typical of a lead-acid battery. Other types of batteries have different cell voltages. They're all going to be somewhere in the neighborhood of 1 to 2 volts, 2.5 volts per cell. Most people don't realize that a lead-acid battery operates in a constant process of charge and discharge. When a battery is connected to a load that needs electricity, such as a starter in your car, current flows from the battery begins to discharge. In the reverse process, a battery becomes charged when current flows back into it, restoring the chemical difference between the plates. This happens when you're driving without any accessories and the alternator puts the current back into the battery. As a battery discharges, the lead plates become more chemically alike. The acid will become weaker and the voltage will drop. This is the interrelation between the three. Eventually, the battery is so discharged that it can no longer deliver electricity at a useful voltage. Now we're going to look at some types of batteries for industrial use. For switchgear applications, two types of batteries are used typically. Lead acid batteries, which are flooded cells and valve regulated, and nickel cadmium batteries. Lead acid batteries are made in several types. First, you have pasted plate with lead antimony grids. This is a basic lead acid battery as the common automobile battery. However, for switchgear control work, thicker plates and lower gravity of acid provide a longer life. It's also suitable for long-time float charging. The expected life of this battery is from 6 to 14 years, depending on the plate thickness. It is also the lowest cost battery. The second we have is lead calcium battery. This is basically pasted plate construction with antimony replaced by calcium for additional grid strength. It has an expected life of about 25 years. Because of pure lead electrochemical characteristics, it requires slightly different charging voltages. So twice now with pasted plate and lead calcium, we've mentioned the term antimony. So what is antimony? Antimony is a toxic chemical element with the symbol Sb and an atomic number of 51. Just a piece of information you'll probably never use. A lustrous gray metalloid is found in nature mainly as the sulfide mineral stibnite. Antimony compounds have been known since ancient times and were used for cosmetics. Metal antimony was also known, but it was erroneously identified as lead. It was established to be an element around the 17th century. For some time, China has been the largest producer of antimony and its compounds, with most production coming from the Hunan province mine. The industrial methods to produce antimony are roasting and subsequent carbothermal reduction or direct reduction of stibnite with iron. The largest applications for metal antimony are as an alloy material for lead and tin and lead antimony plates in lead acid batteries. Alloying lead and tin with antimony improves the property of the alloys, which are used as solders, bullets, plain bearings. Antimony compounds are prominently an additive for chlorine and bromine containing fire retardants found in many commercial and domestic products. An emerging application is the use of antimony in microelectronics. The next battery we're going to look at is tubular positive. This is also known as an ironclad battery. These batteries are suitable for large stations and long-time load applications. Next we have plant. This is a long life battery with an expected life of 20 to 25 years. In this battery, the positive plate is formed from pure lead. Its short-term rates are somewhat higher and amp hours slightly less as compared to pasted plate types. This is the most expensive lead acid battery. Valve regulated lead acid, or VRLA. This is also known as a maintenance-free battery. The cells of this battery are sealed except for a valve that opens at atmospheric pressure by a pre-selected amount. This battery provides means for recombination of internally generated oxygen and the suppression of hydrogen to limit water usage. The cells of this battery are sealed from the environment unless internal pressure operates a release valve. Round cell batteries. This is a pure lead acid battery that has round cells instead of rectangular cells, as found in conventional batteries. The geometrical shape assures uniform growth while the pure lead grids provide for a slower plate growth as compared to lead calcium or lead antimony. And later when we get into maintenance of batteries, we're going to get in a lot more depth about what we're talking about with plate growth. Finally, we have the nickel cadmium battery. It is constructed with pocket plate cells for switchgear applications. The battery plates have three different construction thicknesses. Medium or thin plate construction is used for switchgear applications. The maintenance of the nickel cadmium battery is less than the maintenance for the lead acid. Its low temperature discharge currents are higher and it can be charged more rapidly than lead acid batteries. The cost of nickel cadmium batteries is higher than lead acid batteries. Finally, we're going to talk a little bit about the charger. We'll go more in depth in later sections and modules, but for now, we just want a quick overview of the charger. Two types of battery chargers are available for switchgear control power. One is known as the trickle charge, which is an unregulated battery charger. The other type is a regulated type. The regulated charger provides longer life, especially for lead acid batteries. The regulated charger is recommended for switchgear applications. The selection of charger equipment should satisfy the following functions simultaneously. It should be able to provide a steady state loads on the battery, self-discharge losses of the battery, and equalizing charges. What happens is there's a lot of things that need to be taken into consideration when we're dealing with figuring out what the best charger is for the applications. It's not as simply as just grabbing a charger off the shelf, is what we want to get you to understand here. Steady state loads are those that require power continuously, such as an indicator light that stays on all the time. Self-discharge losses are due to trickle current, which starts at about 0.25% of the 8-hour rate for lead acid batteries. What happens is there's always some little charge being discharged in a battery, no matter how careful you are about the installation or the application. Self-discharge losses increase with the age of the battery. The equalizing charge is an extended normal charge and is given periodically to ensure that cells are restored to the maximum specific gravity. All lead acid batteries require a monthly equalizing charge except for lead calcium type. Nickel cadmium batteries do not require the equalizing charge. However, it is recommended for occasional boosting. In the sizing of charger equipment, the steady state loads, equalizing charge current, and self-discharge current should be added to arrive at the capacity of the charger. Select a charger with ratings that exceed or equal to the sum of the currents required. So let's review our objective for this module. You should be able to explain the basic terminology and theory associated with electrolytic cells. This concludes Module 1 of the Basic DC Systems Testing and Maintenance course. If you have any questions or need clarification on the information contained in this module before you take the exam, contact the instructor at 972-589-7448. You should now refer to your trainee guide and take the exam. If you fail, the instructor will receive an email and contact you for course remediation and retake.